right, welcome everybody. You survived day one. It gets even more intense as we go into day two. No, it's going to be a great time. I want to start with congratulations and thank you to all of you in the audience. The Gary Smith Memorial Scholarship Endowment has now reached $50,000, you know, in a large part to your effort contributing to this. Thank you so much. So DAC, of course, is an exhibit show, but it's also a research. We had more than almost 700 submissions of papers this year. This is a premier conference for anyone doing research in design automation. We accepted 161 papers from all over the world. You can see the breakdown behind me. It continues, you know, the swing goes back and forth between different countries, and you can see, you know, from the Middle East, from South America, we're getting papers now. North America does dominate, but Asia Pacific is hot on the tail. It's very hard to get a paper in, and you know, huge congratulations to each of you in the audience who got your paper accepted, and to those, try again next year. We'll have you back in San Francisco presenting your paper that year. We have more than 100 sessions of the research track, a lot, of course, on engineering design automation, but we have 9 sessions on embedded software, on IoT, 7 on the IP, emerging business area, a number on security. It's hard to get in, security show, so I mean, try very difficult, no. Security is so important, it really pervasively reaches across all of our products, so we make them easy to use. They're also easy for bad people to abuse and take advantage of us. And so, you know, this has to be designed in from the beginning, so that's really been a big part of DAC in the last couple of years. I mean, automotive, again, it brings in that security concern, and also just pure safety, right? We don't want them to run over us. A lot of sessions on that. And of course, design is what is our first name, design automation. At the pavilion, you saw a bit from Sean O'Kane, the layout, you know, it's SIP trends, and we have, again, the one-on-one very popular with our CEOs. You know, we're going to have Simon beaming in from Japan for the Sky Talk, so that'll be quite interesting. They wanted to do a hologram, but you know, the tech's not quite there, so it's just going to be kind of a Skype video. So that should be pretty exciting. And then, you know, CNNs. This is the big driver, I think, for a lot of design coming up. You know, can we build a computer that can just collect lots and lots of data and then set up a system that, you know, makes good decisions and helps guide, again, our self-driving cars and our IoT systems. So we're going to have a panel session on looking at where CNN's artificial intelligence is today and where it needs to go. And then, of course, the teardown at the end of the day. Poster session. So you've seen a lot of this on the video, but I just want to remind you, you know, there's lots and lots to do at DAC. It's a very overwhelming multimedia experience. The DAC app helps you get around. We have the poster sessions at the end of the day, so you can kind of dip into some of that content. And you know, if there's an event that you'd like to see and you didn't sign up for it yet, check out your DAC app. You know, now you can go on there and just basically add an event, so you don't have to run to the front of the show floor to registration to add something that you'd like to check out. You can do it right from your DAC app. You know, we're getting modern here. We're adding instant signups and so on. So check that out. Now we have a hardware design contest going on where we gave the opportunity to a bunch of design teams to put together design based on an FPGA board. And you can see there the list of teams who were selected to compete. They made the first round. There was 29 teams who entered the contest. 5 of them were selected to the next round. They're going to be on the floor today. You can check out their entries, and a set of judges are going to evaluate the inputs, their submissions tonight, and it will be announced tomorrow, the winners. So this is really exciting. I mean, you know, we've made design so easy that you can do it right at a show, right? And we can take a look at their designs and see what's going on. Thursday, just want to remind you, still time to sign up for training sessions on Thursday to go in depth in some of these areas, verification, C++, using Python. So these sessions are available for you on Thursday. These are, you know, kind of all-day classes. So a good way to get deep into the technology. And without further ado, I'd like to introduce Chuck Grindstaff, who's the executive chairman of the Siemens PLM software group, and have him come to the stage. This is now, Mentor is now a Siemens business, and this is the gentleman who's in charge. Thank you so much, Chuck.
Well, good morning, everybody. It's a pleasure to be here. As you all know, or hopefully you know by now, as of the end of March, Siemens PLM Software and Mentor Graphics, now Mentor, a Siemens company, are together. So this is an exciting time for us. And for me personally, it's really great to have the opportunity to stand in front of DAC and talk about our vision, and also to say thank you to the competitors for suggesting what they think our motivations were and what we're going to do with our products. What I thought I'd do, though, is maybe be clear about what we have in mind. What we have in mind of bringing Mentor together with Siemens PLM Software is to drive the products that Mentor has in the marketplace, whether it's Questra, whether it's Catapult, AFS, and of course Caliber. What we have in mind is driving those products forward and continuing the market leadership of the IC design space and also the systems design. Now, why would we do that? I'll spend some time going through our thesis, what our idea is about the future, and why bringing together what is largely a mechanical design, simulation, manufacturing software tools company together with the electronics and software elements of Mentor. Why would we put those together? Does it make sense? I guess you'll ultimately be the judge. But we think that the forces in the marketplace, the forces that you are faced with and your customers are faced with, are driving exactly the merging of these concepts together in the way that we expect. Now, we start with the thesis that integrated circuits, IC designs, IC capabilities are the heart of innovation. The underpinnings of the digital world, obviously, is compute power, storage, the ability to solve problems both centrally and on the edge of the network that heretofore were not possible. And of course, you gentlemen, ladies, are at the center of driving that innovation, whether your products are dedicated processors, high-performance computing, whether they're part of systems on chips, whether they're part of bigger systems of systems, the integrated circuit really is that core starting point. And we start with that as a foundation of our assumption, our thesis of putting these two companies together. We also, across the marketplace, have many customers, customers like yourselves, but also customers who are OEMs of various products. They are faced with really a challenge of today's world and in the future of digitizing their operations. And of course, you might say, well, companies are already digital. They're already using EDA tools. They've already got systems to digitize their HR systems and finance systems. The fact of the matter is today, that those systems are not as integrated as they could be. When you go across the supply chain, there's information re-entered. When you go across disciplines, we find loss of productivity. The digitalization of a company from start to finish, not only from the design through manufacturing, but from manufacturing into operational phase, will make the difference between success and failure of product companies in the future. Now, why do I say that? Maybe it's obvious to you all, but the trends in the marketplace are large, they are compelling, and they are accelerating. You see a few product examples up there. Wind generation. Siemens obviously makes a lot of stuff. We make a lot of really big things, things like wind generators. When you look at a wind turbine, and you say, okay, well, how does integrated circuit? We know that we're going to have control systems in there to optimize the operation of that wind turbine. What's important, though, is the business model associated with a wind turbine has evolved over the years. Instead of just selling one, we sell capacity, capability, performance of an entire wind farm. And in order to do that, we need these devices connected. We need these devices instrumented such that we can predict failure, we can coordinate activity, we can make sure that the entire wind farm is optimized. Now, to do that, we have to design into products from the very beginning the intelligence that it will be leveraged into the operational phase. So we can transition that business model from simply selling a product to selling a capability over the life of that product in the marketplace. And the fact of the matter is this is happening in every industry, or at least most. Automotive. You know, if you look outside, you'll see cars driving on the road. Most of them are parked in the parking lot. And if you're an automotive company right now and your business model is based on the idea that you're going to generate cars, sell them, make your money there, and then those are going to go be parked in a parking lot 95% of the time, your business model is at risk if your competitor figures out how to bring autonomous driving, instant scheduling together with their production capability and deliver mobility. My kids don't really care about cars. Well, my son does. My daughters don't. The fact of the matter is they just want to go from place to place. And they want their app to call up a conveyance system and get them from the airport to the school, from school to work. And if a company is based on this idea, I've got to get all my products into a marketplace that is basically oversaturated, and their competitors are able to monetize the operational phase of that vehicle. So not just the money at the point of sale, but make money throughout the lifetime of that car, completely and profoundly changes what a car company can be, what an automotive OEM is. And in fact, when those things are then integrated into an operation in a city and the like, we have new capabilities, new product abilities and features and functions. And in fact, in today's world, you really, I think, have these two basic concepts. And I saw there's great conference topics on IoT. You know, whether you believe the 10 trillion number or the large number of connected devices that are predicted, the fact of the matter is this is a big impact. The fact of the matter is that products are being designed today in order to be connected so that we can add features and functions that make others want to buy those products, but more importantly, so those products can work in tandem and in sync and as part of a system of systems. And that trend is here to stay and here to accelerate. But I also mentioned this notion of digital and digital transformation of business models. That threat is also there, that opportunity and threat. You see the comment here from Accenture. Digital is the main reason over half of the companies in the Fortune 500 will have disappeared by the year 2000. Now, since the year 2000, excuse me. What his thesis is that if you can't make the transition, if you can't find ways to look at disciplines, integrate them together digitally, you are at a competitive disadvantage. You're not able to innovate fast. And you know, the audience here knows better than most what fast innovation means. The fact of the matter is many of the other technologies that our customers have at their disposal today are evolving on these exponential curves that you all have been living for the last 40, 50 years. And that's what this chart shows. You know, you see some simple product categories. There's some fun ones. I saw you guys going to do a tear down of a drone. That's cool. But when you look at what you all have been doing, you know, driving down the cost of technology via the strong set of tools and engineering and capacity, moving down lower and lower and taking advantage of physics and physical properties to get that density and cost down. We see similar kinds of things being driven in other tools. You see 3D printing. What's happening here is instead of dedicated fixed purpose manufacturing facilities, the ability to use fabrication techniques that have not been possible before are now reaching production level capability and cost. And that improvement is on the same kind of exponential curve as Moore's Law. What we're seeing in digital printing, what we can print ceramics, metal, plastics, the things you can make now are different. The way in which you design products is different. And the rate of change is increasing quickly. So companies are rethinking the kinds of capital allocation that's necessary to their factories. The application of digital printing in the early production means that we have now spare parts and parts delivery that can be done a different way if they're properly certified. Industrial robots. What we did in the past with robotics was we told them what to do very explicitly. You know, bend this joint, twist here, pick something up in that location. Robotics with the distributed decision making, advanced analytics, vision systems, sensors are able now to actually be given much higher level tasks. Go pick things up that look like this. And in fact, now when you integrate them together with people, the sensors and safety systems are such that robots are cobots. And we program now not just the specifics of a joint articulation, but the set of tasks that together with a manufacturing engineer, manufacturer on the shop floor, we'd like done with the robot and the person cooperating in the same space. So this is new. It changes the way people approach automation in their factory. And I won't go through all these, but you know, sensor, the MEMS devices, the ability to ubiquitously put sensors and sensor feedback into products, if properly captured, provides the basis for how we can look at the operation of that product in the field, how we can predict failures, and then optimize operation. Now, the points I've made till now should obviously fit into the next bit pretty seamlessly. Automotive, you know, 80% of the value, the new value in innovation that goes into automotive these days is in electronics and software, 80%. And that's a big change from the way it was 15, 20 years ago. The fact of the matter is that, you know, the 150 or so compute nodes in that automotive network are delivering safety, they're delivering energy recovery, infotainment, a wide variety of features and functions that each of us look for when we purchase a vehicle. And that's just the beginning. The next turn of the crank is applying that really fully to autonomous operation. Now, the driver underneath that, the engineering challenge, is now things that used to be components are not really components anymore, but entire complex systems of systems. Just take the simple notion, you probably all thought of this, but you know, if you go to an electric vehicle, you don't have the waste heat off an engine to drive a heater. So if you're in a cold climate, you have to be very careful to make sure that the heater's not going to run down the batteries so quickly that you don't get to the destination with the electric vehicle. This kind of stuff is pretty obvious, but what it shows is that systems that were in the past relatively distinct and separate need to be designed together. And what makes that possible is a set of integrated circuits and software that can do the power management, that can look and monitor at where things are going, that can make sure that this entire network is able to recover energy in the proper way, use it appropriately, and then operate to within the expected operational limits. Now, we at Siemens have, I think, a relatively similar view to you all about what's necessary to produce a product, whether it's an IC or a board or a system. It really is a flow of information, and we'll talk a little bit about this more later, but the idea is from requirements and systems and those system functions, how do we take the abstractions of that we want embodied in the product, compile those abstractions into something in more detailed fashion, simulate, validate, and then ultimately manufacture. The same exact flow. I mean, obviously the products and the technology and the physics underneath each of those elements is different, but that flow is more and more across disciplines, where we have the software and the electronics and the set of mechanical elements all having to operate together seamlessly, which is putting a large amount of requirements and pressure on what used to be interdisciplinary boundaries, such that we drive more and more co-design. Now, of course, that means we have to be able to not only design the mechanical elements of the product, make sure that the form and the fit and the aesthetics are correct, that it operates right with the environment, that we have the right fluid flow for heating and cooling in this case, but there's also other interactions, air resistance, things like that. So the environmental interaction, the overall electronics design and simulation, all the way down from the board level down to the chip level, and then ultimately take all of those elements together into a complete model of the product that includes the software, that includes the behavioral characteristics that we've built in from the beginnings. So hopefully you're getting a picture of the kind of vision that we have at Siemens. So To this point, you should see that we have an idea of bringing these disciplines together, to being on the cutting edge in IC design, to making sure that we provide the best tools in the marketplace for PCB, software, as well as mechanical, so that we can build that product and be relevant to the entire design community that is embarked upon delivering the next generation product. Now, when they do that, they're going to be part of this ecosystem that's connecting everything to everything else. And again, I think that number used to be 50 billion by 2020. It's come down a little bit. It doesn't matter if it's 26 or 30 or 40. A lot of stuff is getting connected together, and it's getting connected together because of a change in not only what's possible, but in many of the work practices of the systems companies around the world. Many of them are becoming chip designers. Specialty chips, special purpose things, and they are not only looking at providing simple functions on a chip, but also integrating those together with micro electromechanical devices, radio frequency, everything that you need to compute on the edge, and stick that into a sneaker to make sure that you're getting the right number of steps and doing your exercise properly. What's critical about this is that each one of the innovations that we're working on across this spectrum is then integrated into and feeds into these business model changes and propositions that I mentioned earlier. We have 300 companies around the world right now making electric automobiles and trucks. That's on the rise and significantly. Maybe there'll eventually be a shakeout, but the reason that is possible is because the things that you used to have as barriers to entry for an automotive are changing and changing rapidly. So you have new entrants. The things that make a car company successful in the future will be what? That you know how to make the slick exterior? That used to be the only thing that mattered. Then maybe it moved more to infotainment. In the future, it'll be more of the AI technology, the sensor technology, the ability to integrate LiDAR data together with other safety information and deliver an autonomous vehicle and a riding experience that is safer, better than the next. And that has driven many new companies into the automotive industry. I mean, it shouldn't be based on all the stuff that has to happen in that Google car to drive around safely, autonomously. It shouldn't surprise anybody that companies like that are not intimidated by the automotive production side of things, the stamping sheet metal, because the big, heavy-duty engineering is moving more to the AI, electronics, software side. And so that drives companies. We were talking, there's automotive suppliers that are putting in their own foundries, becoming vertically integrated in chip design. So these things are observations that are easy to make, we've made, and the acquisition, the merger together of Siemens PLM and Mentor Graphics is allowing us to serve companies that are across that entire ecosystem. And the idea we have, and the reason that it was imperative, or the driving force about why now, why not 10 years ago, or why not 10 years from now, has to do with this speed of change and where many of our customers are at in this cycle. Taking the IC design, the software continuum, and putting that together, learning from what you all have done in the IC space, leveraging that into the system space, so that we have an entire focus on not only the software, not only the electronics, not only the mechanical, but the entire operating product. It allows us to take concepts like emulation. We've been very successful with our emulation products. Our current Veloce Strato system is, I think, second to none. And in fact, we have future plans to continue to extend it. We have the idea that by learning what we're doing with that degree of emulation and what success has been there, we might be able to apply some of these concepts to take and move to the next level of simulation and emulation of entire systems. The complexity is of a similar scope. We believe that it's absolutely essential that we can, in a very front-loaded fashion, figure out how things will behave before they've been produced. Certainly the amount of focus on mass production has changed dramatically to really the idea of being able to make quantity one at those mass-produced price. So that the idea of being able to configure, drive the flexible manufacturing processes really across the entire supply chain is critical. Now, our customers are often producing tools, and in this case ASML produces a tool that is often, or hopefully, used by some of you in the room. In order to build that machine, obviously this is a complex electromechanical system that needs every aspect of what I've just described. It needs embedded software, the networks, the control units, the internal monitoring, the external monitoring, the ability to interconnect it with all of your systems and do so in high performance. Our customers expect and require that we can really model and simulate that machine. And in fact, in order to do that, we really have the entire set of assets that is necessary. Wally Rines, the CEO of Mentor, often has said, I've heard him say, and I guess his team remembers, and, that everybody's system is somebody else's component. And I think that's a very true statement. And in fact, the thesis we have is that that will continue to be true into the future. Now, I'll spend a little bit of time on this. So I just here put in the standard V form this flow that I talked about earlier, from requirements into functional design, really design for manufacturing the product, verifying it. This V model that many of us have really at the core of our engineering foundation. When you look at the amount of progress that's happened in the EDA space, the movement up to higher levels of abstraction that was mentioned earlier, allowing things to be designed on the show floor that might really have taken a long time in the past. That same level of abstraction journey we're on in other areas as well. So we're making advances in what we can synthesize from requirements, synthesize from functional designs into control system behavior, into the integration of those control systems with the final product. And what that leads us to is a fully multidisciplinary, integrated design process and practice that our customers can apply, that can take the things that we do in IC design, or we do in software design, or we do in electronics PCB, we do in architecture, and do that across every element of the product. Now, you might say, well, okay, that's a big that's a big job. The fact of the matter is, again, our customers are already trying to climb this hill, and they're doing it with systems that are, in some cases, well integrated, and in other cases, not so well integrated. Our idea is that together, our intellectual property can be combined together. We can leverage what we have learned from one industry, one design practice, into another, and in effect move the entire product space, whether you're making a nuclear submarine, or whether you're making a cell phone, or whether you're making a computer, that the basic principles of, obviously there's different physics and different technologies that we care about in one domain, car, automotive versus aerospace, but at the end of the day, the core data flows, the core regulatory requirements that we need to be able to adhere to. Safety was mentioned. If we're in automotive, everything that you do fits into the software, into the systems and control systems, into the validation and verification, so that we can actually verify that what is supposed to happen has been designed, it's been tested, and there's a trace all the way back. So, taking something like ISO 26262, which is the international standard for safety and validation and verification, and making all of the attributes of the product part of that flow, makes it possible for customers to design a product, validate it, and then even report to the regulatory agencies. Well, the good news is if you can do that, if you can put that product together and work really from the entire functional model all the way through the detailed behavioral and tested models, you have a pretty interesting view of how a product should operate. And that data model, that functional and behavioral model, represents the template for operational characteristics of the final product. So maybe I'll try to bring you all back to IoT here for a second. So if we have a car and it's connected to the internet and we want to know whether it's operating properly, it's probably safe to say that if we know it's a car and we got all the sensor data, that's a good hint that the thousands of sensors that are coming in are part of a car. That's hint number one. Hint number two, if we want to see whether that car is operating properly, well, we can look at the various signals that are coming from the sensors and we can say, well, that one's different. It's used to be at one level, it was in this operating band, and now it's got an anomaly in it. Maybe something's going wrong. Well, but that may not be the case. It may be that we drove a car from Dallas to Austin in this heat out here, and maybe there's an ambient temperature impulse to the vehicle, and that anomalous behavior is appropriate for the sweltering heat that's out right now, and it's been designed in. So I would make the claim that the system model, the functional model, the set of operating conditions on those control systems are the data-driven core of the next generation of analytics. So when we look at those sensors, we have a place and a way to integrate them together into a coherent whole and find out, well, yeah, that one sensor is spiking, but that's okay because we have another part of the control system that's there to handle and adapt and adopt to it. So we call that data-driven analytics. So we combine together the data-driven analytics, where we just look at anomalies and changes and sensor feedback, with model-driven analytics, where we take this complete model and integrate it together with those data-driven analytics. The integration of that allows us to take that information into the cloud. We have a great platform for this that brings the simulated data, what we've tested in the lab, into what we call MindSphere. So MindSphere is a cloud platform that allows us to collect the raw data. It also allows us to house and harness the models that have come out of the design systems and merge those and meld those together. As you know, Siemens makes a lot of stuff. They make a lot of products, and we've got a already significant installed base of connected devices to our MindSphere platform as a result of that, where we've taken those system models, we've taken the connectivity capabilities that are coming off the factory floor, connect those together and allow our customers to look at behaviors and to be able to assess performance and optimize performance directly in the field. And of course, this method of publishing how that product is supposed to operate represents a very explicit language of domain know-how that can go to the cloud. So it allows the designers to actually instruct the cloud analytics how and what to think about the various flows of information. And of course, that allows us to bring this model-based analytics concept directly together. So the idea here is the world is moving to more of a systems of systems. IC innovation is at the foundation of the transformation, and the ultimate solution across the multidisciplinary product gives us the analytic insight to drive the future performance, features, and optimization of those products and utilization. Now, the good news is I blasted through this presentation at 100 miles a minute, so we have some time for questions. So that's the end of the prepared slides. And what I'd like to do is open it up to some questions, and you may have some specifically about the merger, clarification of what I just tried to describe. Really, it's up to you.
Okay, and there are microphones right here, so one on each side. Anyone with a question?
There's got to be a question.
Over on the side there.
Okay.
Can you come around to the microphones? They're in the middle hallway. Oh, there's someone standing. Go ahead.
Hi, I have a question about your thoughts on the future of merging OT and IT, and with your merger, what are your thoughts on that?
Yeah, so obviously we have a very deep practice in operational technology, OT, and the fact of the matter is that we see a convergence. Obviously there's different security concerns in the factory. There's different layers of command and control and optimization, but certainly at a high level of abstraction, they're very much the same as optimizing that wind farm to the problem of optimizing a robot garden. We really want to have some of the same techniques and technologies used across, and then you layer on top of it the different security model, different needs for real-time operational guarantees and the like. I ultimately believe that much of the, I hate to give an exact percentage, but 80%-ish of the same technology that we want to apply in OT is applicable in the future to really sort of general IT and the cloud-based future of IoT.
About 20 years ago, in a keynote, Joe Costello articulated a vision moving from EDA to EPDA, electronic product design automation.
Yeah.
Some of the concepts there you articulated today without the IoT, because IoT did not exist then. So the question really is, how do you see electrical, software, mechanical, all coming together in combination with manufacturing and Camstar or Valor and all this kind of stuff?
Yeah, I didn't, in this presentation, we didn't talk a lot about the manufacturing side. I mean, this is a huge part of our business, is how you take the products. I sort of divide the product development life cycle into 3 big pieces. One is you might call it ideation, I often do. So how do you get your ideas captured, modeled, simulated to the point where you've made design decisions and you are ready to commit to manufacturing. There's in the realization of that product. We commit our ideas, they're tested, we've got all of our front-loaded simulation, we know what we want to produce, we try to realize that. And obviously there might be yield issues or production speed and ramp issues that we want to learn out to get the product to full production capacity. But that ideation phase, realization, and then utilization. So the question about that you mentioned Camstar, it makes me want to talk a little bit about the manufacturing, that realization phase. Often you can think of a factory, a big automotive factory, as just a large complex machine. It's just more interactions of more and more in the future, autonomous decision-making devices that are interacting together to achieve some goal. So what we see is the design of the products themselves, the components, the smart elements that are getting more and more intelligent, so we can give them task-directed activities like go here, pick up things that look like that, integrated together into arrays and gardens of flexible devices being very, very similar, the same fundamental problem as what we would do with a car, where we wanted to interoperate through a system of rules and regulations safely on the road and get people from point A to point B, a task-oriented goal. So some of the same logic, the same underpinnings, the same AI technology is applicable to both.
So I have a question in terms of your competition. What does acquisition of Mentor do to your competitive position? And also, do you think there will be further acquisitions in this space where more of the companies that are doing systems design will go after the smaller EDA companies?
Well, I feel very good about the improvement to both Mentor's competitive position and Siemens PLM's competitive position by putting these technologies together and learning from the colleagues on both sides. Obviously it puts pressure on partnerships that we have. Mentor has partnerships with other CAD, PLM companies. Siemens PLM has partnerships with other EDA companies. Those can and should still thrive and survive. I think the real thing is, what can we do on the sort of mechanical side, the PDM side, the collaboration side, and to make our systems more open as we work together with the Mentor colleagues, hopefully to improve the open systems interfaces. You maybe know that we pride ourselves on having an open architecture and being agnostic to the actual vendor when it comes to whether that we allow them to connect to our products or not. And I think Mentor also has a similar, let's do things modular, let's do things in an open fashion so we can plug and play together with the competition. So we'll focus on that, and the competitive value that happens when we're together is we can share ideas. We now have colleagues that we can say, what really bugged you about us as a PLM vendor when you were trying to deal with us before? And we can also articulate what things really impeded our progress. Now, to your question, will others do this? I don't know how they'll avoid it, to tell you the truth. If you look across, you're sitting on a chair that's not electromechanical. Maybe it will be in the future. Maybe it'll give you diagnosis in the future or tell you how much weight you should lose. But besides that chair you're sitting on, most everything is a fully integrated set of electromechanical capabilities. And I don't know any other company right now that's assembled the assets. Obviously we're not done with all the integration. Often when we acquire a company, the next week we get hit from all the customers. Okay, well, why is this fully integrated yet? It's not fully integrated yet. We'll work towards the future. But I don't know, if I was a competitor, I'd be a little bit unnerved that that together with Mentor, Siemens PLM, will be able to do things that I might want to do, and my partnership might not be able to really allow the interdependence and drive the openness that we need. So I don't know. I don't know. We'll see. I would guess so. Yeah.
Maybe a couple of leaps of logic in this, but we seem to be moving from mass production to mass customization, and I guess you'd have a lot of opinions about that, but where I'd like to take you is, are the people coming out of the universities prepared for the new stage of design as we make these kinds of shifts? And what Siemens doing to encourage, stimulate, or adapt to that?
Well, there was a implied mass customization message in my stuff, although I didn't highlight it specifically. The ability to drive configuration, options, variants, to do that at scale, you really need the ability to drive all of these tools together and prove that it's not only valid from an engineering perspective, it's valid from a financial perspective, safety perspective. Has the customized product I'm selling you, is that been properly documented to the regulatory authorities? Blah 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 blah. So, there really is a lot of what's necessary to drive there: further flexibility in manufacturing, further flexibility in products, ability to have instant-on simulation and so forth. Now, when we talk about the next generation workforce, I think technically they're really being educated with, certainly at the university level, the strong technical skills that are necessary. The difficulty is a lot of times they're put immediately into relatively deep and narrow specialty areas, as opposed to the broad systems work or blank sheet of paper work that many of the older generation engineers did. There's probably people in the room here that were working on ICs back when you laid things out on tape, and the ability to go through all, or not ability, but the advantage of going through all the generations of technology, knowing what is possible, and as we move to higher levels of abstraction, being able to connect the dots effectively to the design approach is calming and allows people to make possible changes and make leaps that might be not so possible when people are down narrow pathways. Where we see the biggest challenge with the next generation is not so much at the sort of highly technical, physics, engineering, math students that you might be hiring at your companies, but kind of down a tier, the journeyman level that would work in a factory of today needs to be a computer expert. It's not somebody with a hammer hitting metal. Needs to understand networks, needs to understand programming, needs to be able to help diagnose and run diagnostics on things that are going wrong. And so across our customer base, the biggest challenge is that next tier down, not precisely the top tier designers, but that next tier down, getting out of school those that are interested and have the right skills for those jobs. What we're doing is a lot of work with universities, but also with middle schools and junior colleges across the entire spectrum, making sure that the kids coming out of university have access to the best and brightest tools so they can come and be up to speed quickly, and then making sure that there are technical, not necessarily apprenticeships, but something akin to that through the community colleges. So we donate software, we donate curricula, and we're involved in helping to move back up, not only here in the US, but around the world.
We heard about GE transformation, so I think Siemens to the as an audience is kind of similar. So would you please share any key things Siemens can distinguish it, can do for customers, but others, like including GE, can yet?
Okay. Well, I wish GE good luck. They got a long way to go. I described the utilization phase of a product, which is, if you look at GE's platform, they're really focused on how do you optimize and operate a product connected to the Predix platform. Great. I tried to make the point, maybe I didn't drive it home enough, but I tried to make the point that not just letting the data speak for itself, not just data-driven analytics are necessary, but also model-driven analytics. And GE's got zip, zero, nada, that can do that. So if you want to know how we can help you differently than GE, if you want to merge together data-driven analytics, that is statistics, correlation, pattern recognition, with your model intelligence, if you want to merge those two worlds together, I think you come to Siemens. Okay? And good luck to them.
So I think GE is a good example. To what degree, as a tools company within a large quote-unquote OEM, you have products as well, do you feel that is a challenge? Because in some sense, GE is your customer. And
Yep. Yeah, so actually GE is our customer, certainly on the gas turbine engine side. They use our tools very, very deeply in their product design. Look, we, 10, 11 years ago, we came into Siemens. And as an American software company coming into a German industrial conglomerate, there was a lot of speculation. At the time, the competitors said, Siemens doesn't really want software. They didn't want PLM, they didn't want CAD, all they wanted was Technomatics, blah, 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 blah. Same kind of FUD that we hear about what the competitors think we're going to do with all of our wonderful products together. What we found is actually just the opposite. And, I guess as, somebody who lived it, part of the whole thing being the architect of this deal, I wouldn't have suggested to Siemens that we combine these companies together, put these billions of dollars in the pot if Siemens didn't understand how to nurture and grow the future software business. Siemens sees digital enterprise software, that is the software that underpins manufacturers, product companies, as being the future of the company. And you'll listen to Joe Kaeser talk, you'll hear digitalization, that's the code word that he uses for software in the business, as being a major focus. It's one of three fundamental concepts that Siemens builds its future on. And the other two, just for your info, are electrification and automation. So one level, Siemens is a target-rich environment for us to sell our tools. That we have to provide value to them. If you're going to do a new power plant, we want them to use our design tools. If you're going to do a new wind turbine, we want them to use our design systems. On the other hand, they also represent a company that, the rest of Siemens, represents a company that has deep engineering expertise. I think their engineering is well respected, and we're able to share very openly what challenges they have, what things they'd like to see in the next generation products. So we have kind of an inside view, and most customers are pretty forthcoming, in taking beta software and giving feedback and the like. But there's a degree of sharing that we can do with other Siemens divisions that's not possible really across the corporate boundary. We've had developers, we've had engineers come in and sit with our developers for extended periods of time to work on particular problems, and that's helped us be more relevant.
I think you are talking about the model-driven system building and validation. And I wonder, are there mathematical foundation for your model, or which mathematical theory will be behind your model?
Well, I guess if I understand the question exactly, so you say, which mathematical theory would underpin the model? It's a multidisciplinary model. We have everything from the structural characteristics, the dynamics, how the thing flexes, how it vibrates, how it interacts with fluids, so the dynamics of heat flow and wind resistance. We have the electronics simulation that is underpinning that provides heat sources, but also then the operational simulation of the digital circuitry itself, all the way down to the software. So there's multiple domains of simulation that are stitched together. The challenge is, and why we're not done, why I'm standing up here after being in this business for 40 years and still talking about the future, is because when you take all those mathematical elements and stitch them together, you still want to be able to answer questions that cross over those domains without having to have specialty models in each spot. You want to be able to have a system model and have the various simulations and validations feed into that relatively transparently. So we need to move the abstraction, continue to move it up layer after layer. And we will keep that up. So there's not a single mathematical foundation. If you look at finite element analysis and what we do on the structural side, that's very different than what we do in the simulation and fluid flow side, where you have volumetric and so forth. Okay. I think we used up my other time on questions. Thank you very much.
Hang on, I got a plaque for you. I'm going to present this to you. So I want to really thank Chuck for giving this view into his company. And one of the things that was awesome is, this is mind expanding. I've seen this, our industry has been, totally focused on design and verification of this chip that was all by itself, right? Now we're seeing the integration of our industry, all the technology, blending together into a single space. And Chuck, I thank you for doing the merger in a time frame where we could really get the deep explanation right here in Austin. Yep. Everyone who's deeply interested in this could hear it from the guy who made it all happen.
Excellent. Thank you very much. Appreciate the invite.
One more picture.
Okay, thanks.
All right, enjoy DAC.